Okay, I thought I would do a short little video, hopefully short little video on exponential and log functions, and this would be chapter 4. I've got the worksheets, and I've also found, let us just say, I've also found a copy of another file that might be of interest to us, and we'll work some problems from it at the end of the video. You want to pay attention particularly to that. Okay, we began with the general exponential function base a, where a is anything greater than 1. They all have this shape, whether it's 2 to the x, e to the x, 10 to the x, 100 to the x. They all have that same shape. Now, what do we know? We know that as x goes to minus infinity, the y values go to 0. They're going to approach the x-axis, but never cross the x-axis. We have also seen in class that as x goes to infinity, y goes to infinity and fast. As x gets bigger, the y values get bigger tremendously fast. Now, the domain, and this is important, the domain is a set of all reals, and the range from 0 to infinity. That's going to be useful in a minute when we look at the inverse, which is the log function. Now, this function is always increasing, which means it's 1 to 1. And finally, a little useful thing here, a to the x can never be 0. Okay, now from this, if we look at the line y equals x, and if we were to fold the paper here along the line y equal x, then we would get this curve here. And this is the graph of the inverse, which in our notation is y equals log base a of x. Now, let's look at a graph of this function just by itself. On the exponential, we know that it crosses the y-axis. That's the y-intercept of 0, 1. So that means, remember, we swap x and y, so 1 and 0 has to be on the graph of y equals log base a of x. Now, the domain, well, the x values for the inverse has to be equal to the y values in the exponential function. So the domain is going to be from 0 to infinity, and then the range is going to be all reals. Now this function is always increasing, and that means it is 1 to 1, of course. Now we see here that as x goes to infinity, y goes to infinity, but the y values increase slowly. Okay? Now, what else is there? Well, there's properties. We have the composition properties. That looks like log base a of a to the x. That has to be equal to x, and there's no restriction on x. X can be anything. We also have a to the power of log base a of x, and that has to be x. Now there is a restriction. X has to be positive because you're taking the log of that, and that is due to the domain here. And then we have log base A of 1 is always 0. And finally, your book calls this laws. They're still just properties. And we already know these like we discussed in class. These are log base A of a product. That is going to be equal to the sum of the logs. If we take the log of a quotient, then we subtract the logs. Remember, this all makes sense because a logarithm is just an exponent. And finally, we have log base A of m raised to the power of r. This is going to be r times log base A of m. And that's it. That is all you need to do any problem in chapter 4. It's really very simple, very pretty, actually. And very precise. So I have this same information written up, and it's in one of the sections that are on Canvas. Okay, so let's start on the worksheets. And as we saw in class on Friday, many of these problems can be worked very, very quickly. So we'll go from there. All right, here's a worksheet from 4.1 and 4.2. And we're just going to do some of these. Look at number 2, for instance. We want to graph e to the x and e to the minus x on the same set. Well, remember, e is a number that's roughly 2.71. So e is bigger than 1. So the graph of e to the x is going to be very similar, same shape as 2 to the x. And it's going to cross at the point 0, 1. That's the y-intercept. Well, now what if we want to graph e to the minus x? Well, if you compare it to e to the x, we simply replace that x with minus x, and all that's going to do is reflect it about the y-axis. So this is the graph, the sketch for e to the x, and this is the sketch for e to the minus x. All the little rules for shifting and translating apply here just like they did in previous sections. Now look at number 3. Find the domain range y-intercept of this graph here. Well, now we can do this in any order. Here's what I like to do. I'm going to do this in pencil. I'm going to dot in the graph of the reference curve, which is e to the x. And I'm going to pay attention to this y-intercept, which is 0, 1. So I'm going to figure out where this point is shifted, and then everything else follows. And as we saw in class, we can take this in any order we wish to. So let's just start here. What we did, we replaced x with x minus 2. That's going to slide the curve 2 units to the right. Okay, and then plus 3. So now this is a y value of 1. So this is the point 2 and 1. And now the plus 3 is just going to move it up so that it's going to be located at 2 and 4. But now that's not everything that gets moved. If you look at the reference curve, it is going to approach the x-axis as x goes to minus infinity. So this x-axis, this boundary, this lower boundary, also gets moved 3 units up. So if this is the point 2 with a y value of 4, our boundary gets moved to y equals 3. And then we just sketch in the curve. Like that. So that's going to be a sketch of the new curve. But now look what we're asked to find here. We want to find the domain, range, y-intercept, and graph. That means we're asked to come up with this point right here. Well, first for the domain, that's going to be all real numbers. Just because we replaced x with x minus 2, that doesn't affect anything. There are no restrictions on x. The range is going to be interesting, isn't it? We're going to get every y value from 3 to infinity because of that 3 there. Now for the y-intercept. What happens at a y-intercept? Well, at a y-intercept, x is 0. So if we plug 0 in, we get f of 0 is equal to e to the minus 2 plus 3. So this y-intercept is going to be at 0 and e to the minus 2 plus 3. Now that's just a number. I don't know what it is. We could take a calculator and approximate it. But all you do is you let x equal 0. So that is the y-intercept. Let's jump down here to number 5. Look what it says here to factor this. Or maybe we ought to do 4. What's this going to be? If we use, in number 4, if we use the FOIL method, we get e to the x times e to the x. And remember, you add exponents. So this would be e to the x plus x, or e to the 2x. And then we get a minus 2 e to the x, a minus 15 e to the x, plus a 30. So this thing is going to be e to the 2x minus 17 e to the x minus 30. Now, number 5, we want to go opposite of this. So after seeing number 4, I'm going to guess this is going to be an e to the x and an e to the x. Now, I want the factors of 21, which add up to 10. Now, since this sign is positive, when this sign is a plus, they'll both be whatever the middle is. So I want the factors of 21, which will add up to 10. So those are 3 and 7. So I've factored it. Cool. We could do this one. I bet you can figure out what's going to happen here. This is e to the 3x. This is e to the 3x, right? Again, this is positive, so they'll both be negative. Now, I want the factors of 10, which add up to 7, and that's going to be just 2 and 5. Piece of cake. Okay, now let's look down here at number 6. It says find the difference quotient for f of x equals e to the x. Well, we're going to do this. We want to find this. That's going to be f of a plus h minus f of a over h. That's what we want to find. So what does f of a plus h mean? It's just a set of directions. It means in the function f, wherever you have an x, you're going to put a plus h. So this is going to be e to the a plus h minus f of a. That's going to be e to the power a. Now it's all over h. And it doesn't look like there's much that can be done with this. We can do a little more, because now I want to use this property. A to the m plus n is a to the m times a to the n. So we can go and do this. This is e to the a times e to the h minus then e to the power a all over h. So one last step, we can factor in e to the a out. That'll be e to the h minus 1 over h. Now, something really interesting happens here. When we were looking at this difference quotients for polynomials, remember we knew that if we did everything correctly, this h would cancel. Well, that doesn't happen here. That doesn't happen here. Something else is going to happen. And to discuss that, to discuss what we do with this to try to handle it, well, see you in Calc 1. All right, let's look at some problems from section 4.3, and this is just on log functions. The first problem, it says graph the function log x, or natural log of x. Well, that's log base e, and we don't care what the base is as long as it's greater than 1. The graph looks like this. It has an x-intercept of 1, 0, and there is no y-intercept. So now look, we want to graph this. Well, compare the two. What we did, we replaced x with x minus 4. That means we're going to shift it 4 units to the right. So this point here is now going to be, if we extend this a little bit, it's not going to be at 4. We have to move it 4 units, 4 and 1, so it moves 5. So that point is now going to be right there. But see, the y-axis is a boundary line. It's an asymptote. Well, as x goes to 0, this goes to minus infinity in the y direction. So this boundary line gets moved 4 units over also. And now we can sketch the graph. Okay? And finally, what does the plus 3 do? Well, it's going to take this point 5 and 0 and move it up to 5 and 3. So if we put all that together, we're going to get a curve that has this general shape. And maybe I can make that in green. It's just going to be my curve here, shifted up 3 units. Like that. So to fill in the ancillaries, the domain is going to be anything positive. The range is going to be everything. The vertical asymptote is the y-axis, or x equals 0. And the x-intercept is at 1, 0. Remember, an intercept is a coordinate. X equals 1 would be incorrect. Now the domain here is going to be what? Instead of 0 to infinity, like here, it's going to be 4 to infinity. Okay, because of that x minus 4. The range is still going to be minus infinity to infinity, and the vertical asymptote is going to be x equals 4. So same old game, just left and right, up and down, piece of cake. Okay, problem 2, find the domain. Now, people have trouble with these. They're the simplest thing in the world. Just do this. You've got the natural log of something. Just cover that something up. Just cover it up. If you compare it to the reference, and this is my reference curve, log x, the domain is 0 to infinity. Regardless of what we take the natural log of, no matter what that argument is, it has to be positive. So what's going to go on here? We have to have 7 minus x is positive. So that means 7 is greater than x, or x is less than 7. So the domain, I'm going to squeeze it in right here. The domain would be what? Minus infinity to 7. So these are no big deal. You just take this, and the condition is it has to be positive. So that means x will be greater than minus 9 over 2. So here the domain of f would be what? Be minus 9 over 2 to infinity. Here, the domain is everything. The cool thing about exponentials, unless there's something weird up here like a square root or something, that's just a polynomial. See, cover the base up. That's a polynomial. You can plug anything into the polynomial. So the domain here is everything. Finally, it says compute without a calculator. Well, we're going to go back and use those properties that I started the video with. Okay? So you want to write this as log base 7, and you want to write 49 as 7 squared. So it's just 2. Log base 2 of 64 is log base 2 of 2 to the 6th. So that's just a 6. Log base 5 square root of 5 is log base 5. 5 to the 1/2. So it's going to be 1/2. Natural log of e to the 9th, that's just a 9. E to the natural log of 8, 8. Log base 3 of 1, 0. Now look at this one. Look at h. We wish to write this as the natural log of e to the minus 6, and that becomes just minus 6. Natural log of 1 is 0. Log base 10 of 1 is 0. This is going to be log base 10 of 10 to the 1, 2, 3, 4, 10 to the minus 4, so that's minus 4. And you should be able to shake and bake just as quick as I did on those. Okay, 4-3. Next. All right, section 4.4, properties of logs, or what your book calls laws of logarithms. And look at what we've got here. We've got log base 3, and we're subtracting. So this is going to be log base 3, 36 over 4. Well, 36 over 4 is 9. And guess what? That becomes log base 3 of 3 squared. So the original problem statement is just kind of a crazy way to write 2. Let's do B. We're going to go through these very quickly. This is going to be log base 6. Now we're adding 2 logs, which means that's going to be multiplication. So that's going to be 3 times 12. That's going to be log base 6 of 36. That's going to be log base 6. Now 36 is 6 squared. And then that's a composition property 2. C, part C, this is log base 5. Now 25 is 5 squared. To the 12th power. Now, this is log base 5 of 5 to the 24th. And what's this? You guessed it. 24. Oh, look at this. This is pretty. Look at this one. So I'm going to cover this part up. This is understood to be base 10. So just cover this up. Cover this up. So I've got log base 10 of 10. And then this inner exponent is 10 to the power of e. Well, remember, when those are the same, we just get a 10 to the power of e. Now let's put this back out in front. Now that's understood to be that, so that's log base 10 of 10 to the e. So just e. There's really not much in these. Okay, look at 2. It says use properties of logs to expand each expression. Well, what do I have in the argument? This is called the argument. I have a product, so this is going to be log base 3 of 9 plus log base 3 of x to the 5th. Now this is log base 3, and guess what? 9 is 3 squared. Now I'm going to use a property and bring my 5 down. And finally, log base 3 of 3 squared is just a 2. So this simplifies to 2 plus 5 times log 3 of x. Oh, let's look at this. Looks nasty, doesn't it? Well, I've got three things multiplied together. So that's going to be three products. That's three products, three things multiplied together. So I'm going to have three sums. This is going to be the natural log x plus 1 to the 1/2 plus the natural log of x minus 3 plus the natural log of e to the 5th. Well, look at all we can do here. Natural log of e to the 5th is 5. So I'm going to put that 5 there. This 1/2 I can bring in front. And then I've got another one term, natural log x minus 3. And that's a cool thing. Very nice. Let's go down here and do D. Let's look at D here. Now I've got the log of a quotient, so that means I'm going to be subtracting logs. But down here I've got a product, which means I'm going to be adding them eventually. So let's write out what this is. This is the natural log of x squared plus 4 minus then the natural log of x minus 7 times x plus 8 cubed. Now you gotta watch your parentheses in this one. We're done with this. There's nothing else that can be done to this. We have no property that is now useful. So I'm going to have minus, but look what I've got. I've got a product. So big parentheses. This will be the natural log of x minus 7 plus then the natural log of x plus 8 cubed. And one more step. Natural log of x squared plus 4. Now I'm going to distribute the minus the natural log of x minus 7, and then the 3 we can put down front. So minus 3 natural log of x plus 8. Very nice. And that's it. That's all you can do. That's all you can do to that one. Now the third one, it says use properties of log to compress this. Okay, so now let's look. I've got 5 times all this garbage in here. See, here's parentheses, and here's its partner way out here. So what I'm going to do is try to see what I can do with all this stuff. Now look here, I've got a sum, which means it's going to be a product. So I'm going to have 5, and I'm going to have log base 4 of x. Now I've got to take this 3 and make that an exponent. Log base 4 x minus 1 cubed. Minus, I'm going to make that an exponent. So this is log base 4 of x plus 2 to the 1/2 minus then log base 4 of 3x. Okay, now you have to get these to where, before I can apply the other properties, I have to make sure these coefficients are 1s. So that's going to be a product. So that's going to be log base 4. And then I'm going to have x times x minus 1 cubed. Okay. Now what about these? So I'm going to factor a minus 1 out. Now when I take that minus out, that becomes a plus. Okay, so this ends up being a product. Okay, so it's going to be minus log, And now I want to multiply this together. So let's write it as 3x, x plus 1/2 to the 1/2. Okay? And now I've got this finally down to the difference of two logs. So this is going to be 5 log. Now this is going to be a big one, isn't it? So this is x times x minus 1 cubed. And then I'm going to get 3x. And now this means the square root, doesn't it? So I'll have a square root x plus 1/2. And finally, this is 5 times that log. So when we're done, the log base 4, I think my pen's about to go, log base 4 of x times x minus 1 cubed, downstairs 3x square root of x plus 1/2, all to the 5th power. Oh my goodness, what a mess. Okay, we have one more worksheet. Okay, now here's the worksheet for section 4.5. So we want to graph this. Well, let's just draw in our reference, which is going to be y equals log base 5 of x. Now we know what that looks like, right? Here's 1. So I'm gonna draw it in with a dotted line. So it's going to have this shape here. Okay, that's our reference line. So let's look at this. What I'm going to do, I'm going to move this point, which is at 1, 0. I'm going to move it 7 units to the left. So it's going to be over here at -6. Now it is asymptotic to the y-axis, which is x equals 0. So that's going to move, I'm just going to extend that. That's going to be moved over also to -7. So the curve has to stay to the right of -7. So the domain, we can answer that. That's going to be -7 to infinity. Okay. Now the range? Well, the range is going to be -infinity to infinity. You're going to get every possible y value. Horizontal asymptote? None. Vertical asymptote is going to be x equals -7. Now, let's investigate here. X-intercept. When we move this thing over, it's going to have some kind of a shape. And see, we're going to move it over this point, and then we've got to move that point 3 units down. So it's going to be somewhere like right here at -6, -3, right? So now notice how this curve comes up here and it breaks to the right. And see, for a small change in x, you're not going to get much of a change in y. It kind of flattens out. Now, it's not horizontal. It's always got some slope, like my pen. But remember, as x goes to infinity, this y goes to infinity, but very slowly. So here's the deal. Let's just think. To get an x-intercept, we got to have y equal to 0. So let's come down here and let's set this equal to 0. Now look at what we're going to get. We're going to get log base 5 x plus 7 minus 3 is equal to 0. So log base 5 of x plus 7 is equal to 3. Okay, well, now what? Well, we don't have any other properties to use, so we have to write the equivalent exponential. So the base is 5, the exponent is 3, and that is equal to x plus 7. Well, 5 cubed is 125, so x, wow, is going to be equal to 118. So it's going to cross the x-axis way the heck out here at 118. So see what's going to happen. If you take this dotted curve, my reference, and draw it this way down, the curve is essentially going to come up here like this, and it's just going to go sideways to where it does that eventually. Holy moly. Wow, look at that. So the x-intercept is going to be 118 and 0. My word. Well, now what happens at a y-intercept? Well, at a y-intercept, x is 0. So just plug 0 in for x, and then the y-intercept is going to be what? 0 and log base 5 of 7, and then subtract 3. Whatever that is. But that's the coordinate. I wasn't expecting that. Look at that. That's a killer. Okay. Problem 2. Solve each equation. Now, this is what we've been working for, so we can handle these. What I'm going to do is write that as 10 over 1 and just cross multiply. So I'll get 1 times 5 is 5. And then I'm going to get 10 times 1 minus e to the x. Now divide by 10. If I divide by 10, I get 1/2 is equal to 1 minus e to the x. So I'm going to move this over here and this over here. So I get e to the x is equal to 1 minus 1/2. So that's e to the x is equal to 1/2. And now to solve for that exponent, I have to use logs. So I'm going to take the natural log of both sides. Remember, the natural log of e to the x just gives me x. So x is equal to the natural log of 1/2. Cool, cool problem. Okay, B. Look what we're going to do here. We're going to have e to the 2x minus 7 e to the x plus 12. And how about this? Look at this. Isn't this pretty? From what we did in an earlier worksheet, we can guess that this is going to be e to the x and e to the x. Now that sign is positive, so they're both negative. And we want the factors of 12, which add up to 7. That's 4 and 3. So that means I have e to the x minus 4 is 0. E to the x equals 4. Natural log of e to the x equals the natural log of 4. So x is equal to the log of 4. Now also we have e to the x minus 3 is 0. So we're going to do the same procedure as this over here and get x is equal to the natural log of 3. Cool. Really neat stuff. Now look at this one. Here. Look at this one. Now watch what happens. This is very, very important. I've got a common factor of x cubed. And I also have a common factor of e to the x. So when I take x cubed to e to the x out of this, I'm left with an x. There's an x cubed e to the x. So I have three things multiplied together that give 0. So I have x cubed can be 0, which means x is 0. Nice. And then I have e to the x equals 0. Impossible. Remember, e to the x can never be 0. So that's silly. And then I have x minus 5 is 0. So x equals 5. So the solutions are 0 and 5. Okay, let's look at this log problem. What have I got? I've got the sum of two logs. So this is going to be log base 4. X times x minus 6 equals 2. And there's nothing else we can do. So what we have to do here is write the equivalent exponential. The base is 4. This thing alone is the exponent. And that's going to be x squared minus 6x. So this becomes x squared minus 6x minus 16 is 0. Okay, so what's going to happen? Well, this is going to be x. It's monic. Now I want the factors of 16, which subtract 2, 6. Well, that's 2 and 8. The middle term is negative, so I make sure the biggest factor, 8, is there. So then this is going to give me x equals 8 or x equals minus 2. Now, you always have to check these. If I plug in, let's go back to the original. If I let x equal 8, that makes sense. And 8 minus 6 is 2. That makes sense. But if we check negative 2, we've got the log base 4. And that does not exist. This has to be positive. So that means this is a spurious or extraneous solution. Your only solution is x equals 8. And let's see if we can't do this last one here. I've got the difference of 2 logs. So this is going to be log base 5 of x plus 20 over x plus 1. And that equals 3. And we're out of things to do, so we can only write the equivalent exponential. So that's 5 cubed base exponent is equal to this mess here. Well, 5 cubed is 125, so we have 125 is equal to x plus 20, x plus 1. Now cross multiply. That gives us 125x plus 125 is equal to x plus 20. So 124x is equal to what? A minus 105. Holy cow. So x is going to be equal to a minus 105 over 124. Phew. Right. And see, that's going to be okay, I think. And let's check this. 5 to the third equals this. 125, cross multiply. That looks good. That looks good. 124 minus 105, so that's 105 over 124, and I don't believe that factors. Well, let's see if it makes sense. If we put negative 105 over 124, now see, this is not one. This is less than 1. This is a fraction, like minus 1/2. If I were to put that in here, this argument, this whole thing becomes positive. And now this is also going to be positive, just barely. So I think that's going to be okay. I don't see a restriction there. So okay, we'll let that go, and well, when I printed out the worksheet for 4.5, I forgot that there were 2 sheets. So I'm going to add a couple of these problems here, and then we'll finally call this thing wrapped up. So let's look at F here real quick. I want to subtract 5 from each side. That's going to give me the natural log of 4x minus 1 is going to equal 30. Now all we can do is write the equivalent exponential. The base is e, the exponent is 30, and that's got to equal 4x minus 1. So now just solve for x. So this would be 1 plus e to the power of 30. is equal to 4x. So x is equal to 1 plus e to the 30th over 4. And folks, that is a fantastically large number. Okay, now g looks kind of interesting, doesn't it? What do you do here? Well, just think of this as something. So you got the log base 3 of something equals minus 1. Write the equivalent exponential. So the base would be 3. The exponent's minus 1. And that's going to be log. Now, am I reading that correctly? That's log base 125 of x. Well, now that's 1/3. And the only thing we can do is, again, write the equivalent exponential equation. So the base is 125. The exponent is 1/3, and that equals x. Well, now this is the cube root of 125. Well, 5 times 5 times 5 is 125. So this original problem was just a fancy way of writing the number 5. I like that. Which one next, you reckon? Let's do h. Now, here, I'm subtracting 2 logs, so this is going to be log base 2, x minus 3 over 2x plus 1. And that's going to be log equal to log base 2 of 4. Well, what can we do now? Remember, the log function is 1-to-1. It's always increasing. So that means log base 2 of something. If that equals log base 2 of something, the somethings have to be equal. Since it is 1-to-1. 1-to-1 is extremely important in mathematics. So let's write that as 4 over 1 and just cross multiply. That'll give me x minus 3 is equal to 4 times 2x plus 1. So that's x minus 3 is equal to 8x plus 4. And we're home free. I'm going to subtract x and add this over, and I'm going to get 7 is 7x. So x is 1. But now look what happens. The mathematics has told us the only way this can occur is when x is 1. But what happens when you put a 1 right here? This becomes the log base 2 of minus 2, which is not possible. This argument must be positive. So when I checked this, we did all this work, and we found that the only way it can work is if x is 1, but x cannot be 1. It makes part of the problem undefined. So there is no solution. And sometimes problems just don't have answers. Let's go down and do k here. Now this is going to be e to the x plus 1 over e to the x is equal to 2. Cool. Now, watch. I'm going to make that 1 and get a common denominator. So that's going to give me an e to the 2x. Remember, you add exponents. E to the 2x plus 1 all over e to the x is equal to 2. Well, write that as 2 over 1. Cross multiply. E to the 2x plus 1 is equal to 2 times e to the x. So that's e to the 2x minus 2e to the x plus 1 is equal to 0. And guess what? This factors. That's going to be e to the x minus 1 times e to the x minus 1. Okay. E to the 2x minus e to the x minus e to the x equals 0. So therefore, we have e to the x minus 1 is equal to 0. So e to the x equals 1. And what is the only power you can raise e to get 1? That's right, 0. So this original equation is just 0. That's a crazy problem, isn't it? Okay, let's wrap it up with J here. First thing I'm going to do, let's go up here to have a little more room. This is 3e to the 2x plus 11e to the x minus 4 is equal to 0. Now, I would be a very happy camper if this factors. So let's see. Let's try 3e to the x and then an e to the x. Now, we've got to make this work, right? My pen's about gone. We've got to make this work. And this sign is negative, so they got to be plus minus. But the middle term is positive, so I'm going to put the plus here. And the minus here. Now, is that going to work? Let's see. I need the factors of 4 along with the factors of 3. That will give me 11. Yeah. If I put a 4 here, that gives me 12e to the x minus an e to the x. Cool. Now look what happens. This means, neat, this means 3 times e to the x minus 1 is 0. So this gives me e to the x is equal to 1/3. Now take the natural log of both sides and you get x is equal to the natural log of 1/3. Very nice. Now this means I have e to the x plus 4 is 0. So e to the x would be minus 4, and that is impossible. Remember, e to the x is always greater than 0. So this is nonsense. So your only answer is that. All right, long overdue. I hope that helps.